observation programs at European Space Agency. Before that, he headed the Science Strategy Office at ESA's Earth Observation Center, ESRIN, in Italy. He also holds a professorship in terrestrial remote sensing at the Department of Geography and of the Ludwig Maximilians University in Munich. So very well. He's got all the credentials that we need. So Michael, if you're ready, you can turn on your video. We're looking forward to hearing your talk from the ESA perspective. Thank you.
Thank you very much, David. Good morning, ladies and gentlemen, dear colleague panelists. It's a great pleasure to be here today and to be able to give you a little bit of glimpse on ESA's Earth observation programs. You've already heard the words of welcome from my director, Josef Aschbacher, who regrets not to be able to be here today, but he had to travel to our ESA Council meeting. Let me try to guide you a little bit through our Earth observation programs at ESA. And I'm trying to get my system to work. I hope you can see it. Earth observation, one of the fastest growing space domains, and that ties very much in with what we've just been able to see in Malcolm's excellent presentation on how quickly the space domain is picking up, is going forward, not only in technical and scientific terms, but also in terms of financial evolutions. Our Earth observation vision is to take the pulse of the planet by means of scientific and societal challenges with European and global partners. And what you see here are Earth system variables such as the ozone distribution in the atmosphere, sea surface temperature, precipitation, forest fires, urban heat islands. With observing those variables with our top class missions, we are trying to raise the understanding of the planet's processes, but also our environment. In order to do that, now this should go further. I don't know why it's coming back. We have 3 satellite families, which you see here in these rings. First and foremost, the innermost ring, the left satellites where you read science. These are our technology and science groundbreaking satellites, the Earth Explorers, with which ever since the early 90s, we are really trying to launch, develop, design, and launch and operate very innovative spacecraft with new measurements to further our understanding about the planet and its environment. In the middle, you see a more than 8 billion euro heavy program that we are carrying out together with the European Union. And those are not exploratory science satellites, right? The opposite. These are operational monitoring satellites in order to sustain and support the services, the policies, and the directives of the European Commission. Those satellites are called Sentinels. So they're on an operational basis serving society. On the right-hand side in orange, you see our meteorological satellites. As a matter of fact, those were the first ones we launched in the early 70s with Meteosat as a first one. Meanwhile, we have a complementary geostationary and polar orbiting program, the METOPS, and the newly evolved Meteosat. Meanwhile, we're working on the 3rd generation, which gives unprecedented weather data that are supporting our weather predictions. Now, I couldn't give this presentation without showing you a few images of Ireland. I was myself involved in Envisat, a big Earth observation flagship satellite, which was launched in 2002. What you see on the left-hand side is very fantastic meandering plankton in the Southern Irish Seas. And this is from Envisat, taken in 2010. So it's an optical imaging spectrometer, an optical satellite, sensitive to the wavelengths to which also our eyes are sensitive. Conversely, on the right-hand side, and of course on the left, we were lucky to have a glimpse, an almost cloud-free glimpse on Ireland. On the right-hand side, we have a radar image, which is mosaic together out of 15 Sentinel-1, so that's from the Copernicus satellite series, the Sentinel's radar, synthetic aperture radar. And those radar beams can go through clouds, and what you see in the western the granity hills and mountains of Ireland in red, the water bodies in blue, and the cities here in yellow at the right-hand side in the east. Of course, you can nicely see the city of Dublin. These are very recent images, and independent of night and cloud coverage, we can establish land cover classes with this kind of satellite. I've just referred to Malcolm's talk already. We do observe that Earth observation has become, in all the space domains, a very, very dynamic domain. Earth observations is at the moment the biggest program that we are having in the European Space Agency. And we have an annual growing market by about 10%. And also the revenues have over the last year climbed from 1.24 billion to 1.38. And we see a bit more than 15% of growth also in employees. And also here I have to refer to the fast growing startups that are using Earth observations in order to support societal services in various realms. The number of companies also has roughly gone up by 11% from 515 to 572. So that's a very healthy and a very stable growth. But we cannot stay still at ESA. We have to pay tribute to that. So our technical revolutions, as I call it, also would mean that we have to invest and look into new observing techniques like small satellites, like just previously been presented, CubeSats, but also complementary observations through high altitude platforms. We are using new ICT techniques such as artificial intelligence and cloud and grid-based techniques to cope with our huge data volumes that we are requiring. And of course, we're using artificial intelligence in space, not only for in-space data processing, but also data reduction in order to make sure that we offload our ground segments a little bit here. At the moment, with the Copernicus program, we are distributing about 250 terabyte of new Earth observation data. Now, unfortunately, the comparison that I'm making with these 250 terabyte is not an Irish one, it's more a British one. Someone told me once the 250 terabyte would be a DVD tower as high as the tower in England, and that times two is the data that we are distributing every day. Of those Sentinels you see depicted here, from Sentinel 1 to Sentinel 6, all of a different character to monitor our environment, from radar via optical to also atmospheric sounders and radar altimetric satellites who measure the sea surface height and its rise. The benefits that are predicted range by 2035 between 67 and 131 billion euro, which is quite a widespread, but with the fast growing market, those numbers are very difficult to predict. However, a very positive trend and of course a boost in European competitiveness. And this Copernicus, a palette of satellites that I'm showing you here on the left, is of course not only there to support our services, but also to support, and we are very much driven by political agendas such as the Paris Agreement, the United Nations Sustainable Development Goals, and of course UNFCCC and IPCC's climate reports and climate observations. Now, this was a very difficult year for many of us, and we have tried in the European Space Agency to make sure that the businesses can run, that industry is kept functional, that satellites are continued to be developed, to be built, and to be launched. And we've had the idea, and that was realized within 2 months, to have a rapid action on COVID-19 and use Earth observations and satellite data for it. So by combining ESA's expertise with European industry skills, we've been showcasing several examples on how with Earth observations you can monitor the impact and the effects of COVID, such as in agriculture, whole asparagus farms remained unharvested, and we saw water quality improvement in the Mediterranean, but also in other coastal zones. We saw the change of habits in manufacturing plants, such as, for instance, motor vehicles. traffic at the border, at customs crossings, parked airplanes. So there were a lot of effects that we saw. And if you go to, I would invite you to race.esa.int, you see these growing examples of COVID effects. We then created a dashboard together with NASA and the Japanese space agency JAXA, who also tied in. And meanwhile, we have more than 100,000 visitors of this rapid action on COVID website. So that's a very interesting example on how you can see how also traffic patterns change in our life. Here, one example how the atmospheric pollution over Central Europe has just halved between March and April 20 as compared, and you see this flipping forward and back slide, as compared to the same months the year before. Not only for COVID, but also, I mentioned climate before, we are using our satellite data, meanwhile, more and more in order to tune in major climate models to show how accurate they are and to see how robust their simulations are. And you see here, first in gray and then in black, the observations that we've been doing, the satellite observations that have been helping us to look at the Arctic oceans go back until the late 70s, early 80s, and have been able to really hinge major climate models, CMIP exercise, so model intercomparison projects to see how our data records help also to tune and calibrate those models, which again give us a clue that, for instance, by the year of 2050 or even a little bit beforehand, in the summer months or end of the summer in September, we will probably have to look at an ice-free Arctic. So for climate, very important. Also in biodiversity here, an example over Indonesia, where deforestation is responsible for a lot of disappearing ecosystems and biodiversity loss. This is what we can also, through thick cloud coverages, make visible with our radar. And the deforestation over Borneo here in this example has been massive over the past, let's say, 20 years. I mean, this series goes until 2018. A similar thing with our climate change initiative, which is trying to establish essential climate variable accuracies by means of Earth observation satellites. What you see here is the retreat of permafrost in northern latitudes up until the year 2019, which is very important also to get a glimpse and a predictability of emissions of methane that we will, as a consequence of the permafrost thaw, encounter in the future. Now, let me go to the next slide. Here we go. One of the most recent exploratory, so no Copernicus operational, but more of the exploratory satellites, is a technology groundbreaking mission where we've tried to have a vacuum laser operating from space to measure wind speeds in upper atmospheric layers up until in the stratosphere by measuring the backscatter of laser from air molecules. And what you see here on the left hand of the image is the model predictions of Hurricane Dorian in August 19. And then you see the observations of Aeolus before the landfall of the hurricane, which gave rise to these green prediction. And the final observations when the hurricane had taken its course was very close to our observation on the right-hand side. You see that the Aeolus wind speeds are now giving a very positive impact in terms of quantifying upper wind speeds in the stratosphere and upper troposphere, which has now caused EUMETSAT, the European Meteorological Weather Satellite Organization, to want an operational one of these technology precursors, Aeolus. So this was a real technology challenge, and what you see here is how this laser flies across the sky, and you see in these vertical profiles the different velocities or wind speeds, wind vectors, basically as a function of altitude. So very accurate and unprecedented measurements. Very often those satellites give rise then to operational sensors, such as we had with our previous synthetic aperture radars, which have now spawned into the operational Sentinel-1, which is showing here the Pine Island Glacier as it's calving and posing a major threat. You may have read in the news to islands a bit further up north, which is huge icebergs of the size of Malta are breaking off and drifting northwards, then this disintegration of the ice shelf. I have a little bit problem with forwarding my slides. I apologize for that. And of course, this also makes National Geographic News. Here, one recent example of the ozone hole in October of this year, which is one of the biggest ones. It's comparable to the ozone hole of 2015 and 2018. Fortunately, not owing to anthropogenic emissions. This time it's a temperature anomaly in the stratosphere. Usually at that time of the year, in December, the stratosphere is warming and is helping to close the ozone hole again. This year it was particularly big, but this is a meteorological phenomenon which we've observed with Sentinel-5 here, which is an atmospheric chemistry mission with which we can see nitrous oxides as emitted from traffic and transport. But in this case, we looked at ozone. The good news is that we are expecting after the Montreal Protocol that the ozone hole will probably close again to its earlier values from decades ago by the year of 2050. Recently, just last month, we have launched Sentinel-6, which is a radar altimeter that is helping, again, with an unprecedented accuracy to measure the distance between the satellite and the sea surface to better than a centimeter, much better than any radar altimeter has done before, and with a higher resolution, which gives us a very good handle on the sea level rise that we've been measuring with radar altimeter since 1992, which is a sort of the undisputable fact that climate change and global warming particularly is happening. And here, this animation, which should have actually gone before. What you see here are the rising sea levels by means of being measured with radar altimeters, which are sort of radar pulses, the return of which from the sea level is being measured very, very accurately, giving us a clue on how the sea level is behaving. On that curve, you see that almost linearly between the early 90s, when we started with radar altimeters, up until the year 2013, we had roughly a 3.1 millimeter per year sea level rise. We are now at the point where it's getting more into an exponential character, that curve. So now we see that we have almost 4.8 millimeter per year. There are from the Academy of Sciences some negative assumptions or forecasts that indicate that it could, over the next 80 years, means until the end of the century, we could have a rise of sea level up to almost 1.3 meter, which is very high. Some people say it's a meter, but basically it's worth watching the sea level continuously with radar altimeters in order to get the accuracy that we need. With Copernicus, however, even though it's an operational series, we are not standing still. We are now developing a new suite that goes beyond what we currently do with the Sentinel. So we have these expansion missions, which now add CO2 monitoring by means of spectroscopy, polar ice and snow topography, sea surface temperature and ice concentrations, but also agricultural management, food security, biodiversity, to the goals that the current Sentinels are covering. And we are developing those for launch from 2027 and beyond onwards. I told you before that we're not only looking into big missions. This September, we have launched our very first small CubeSat mission. And that was a CubeSat with a small artificial intelligence chip, which is trying to make cloud masks. On the left-hand side, you see the image that this relatively coarse spectrometer was taking up. And on the right-hand side, you see the superimposed calculation of this AI chip on the image cube. In blue, no clouds, and the denser the cloud gets, the more yellow it appears in this artificial intelligence processed image. We are using AI, meanwhile, also to have spectral features extracted to give us a better handle on diagnosing what kind of materials we see in a hyperspectral image, for instance. These were those FSS SCADs or FSATs. These are usually in the class of 2 to 3 million or 1 to 2 million euros per CubeSat. We have a small mission line added to our program, the so-called Scouts. You see here the first four hot candidates for the Scout selection. We've just 2 weeks ago at program board selected the first of those four, which is ESP Max. It's an Earth System Processes mission trying to monitor atmospheric compounds by means of a constellation of CubeSats. We are not dropping the other three. We are trying to continue work on those. But the first one selected, and here we're talking about a 30 million euro machine, so still comparably small, but we're looking at a fast turnaround time and a relative quick launch from the start of the feasibility study. Now, complementing all those satellite efforts, we have a program that we call Incube, the so-called ESA Public-Private Partnership Program, in which we are trying to, with a matched funding from the different member states, to get small missions, but also exploitation programs, application programs, by giving not only our name and logo and stamp of credibility, but also personalized guidance with our expertise, and of course commercial support for new developments. Of course, through membership in the Incube community, which is a small program that we have, the community or the member states representatives get also access to our networks and dedicated events, such as the FELAB that we have here in Esrin, and of course to all our other Earth observation facilities we have in ESA. One of our most recent endeavors is to simulate the Earth through a physical representation of it, which is very accurate, called a digital twin. Many of you may know digital twins from engineering, like before you develop to see the thermal loads and also the forces. We are trying for Earth to undertake a much more complicated endeavor. That means to combine observations from space, but also commercial and public, together with Earth system science and artificial intelligence to make a physical representation of the Earth in the form of a digital twin, to raise our scientific knowledge and help us simulate the processes of planet Earth, but also to find intelligent solutions for our prognostic capabilities and predictions. This would enable us to also give information to stakeholders and decision makers in which way the planet might evolve under certain conditions. And that's one of the most recent endeavors that we undertake, and it's a very challenging one because the Earth system with its different spheres, hydrosphere, geosphere, biosphere, atmosphere, and cryosphere, is very, very difficult to establish such a digital twin of. With that, I've come to the end, and I would thank you very much for your attention and hand back to you, David. Thank you.
Thank you very much, Michael. I mean, I really love just watching the overlays in the videos, and so it's so visual, and to be able to show this data and have it kind of inform policy or be used for research or for forming companies and stuff. It's very exciting, but beautiful slides to be showing. So thanks again. And again, I'll encourage people, we have some questions coming in that I'm keeping in my pocket for the Q&A at the end. But again, there's still time to bring in questions for anybody. So next up, we have a Kira Bartley. Kira Bartley serves as the head of the Irish delegation to the European Space Agency. She manages the Irish input to the EU space policy and the coordination of the national space policy. She's based in the Department of Enterprise, Trade and Employment, and she led the development of Ireland's first national space strategy for enterprise that was published last year. So a lot of you have seen it. Kira, I'm going to hand over the screen to you.